Hello, welcome to a video on pages 5 and 6 of the section 3.4 notes. So we'll start with example 4. So your total model rocket goes off vertically with launch velocity of 160 feet per second. Its height s feet above the launch pad at time t seconds is given by the following equation. So the first step, you're told how high does it go? Well, one thing that might help is that we can graph this equation. Remember, it's the position function, so that's s and that's t. Of course, s is in feet and t is in seconds. Now, if I factor out a negative 16 and a t, I get that. And if I set the position equal to 0, t equals 0 or 10. So we see that crosses the x-axis at these two locations. And because it's a parabola that opens down, this is the shape of the curve. So this is the path basically that the rocket will follow, where that's 0 and that's 10. So you're asked to determine how high does it go. Well, of course, this is the peak. We're not quite sure what the coordinates are just yet. Now, you could get away without having to use any calculus here, because if you think about it, if you want to ensure the symmetry, because x equals 0, x equals 10 both have the same y coordinate is 0, then the x coordinate of the vertex would have to be 5 in order to guarantee the symmetry. And then, of course, you find s of 5, work it out, and you get 400 feet. So that's how high it goes. Now, there's also a calculus way of looking at it. What if I drew a tangent line at the peak? We know the slope of the tangent line is 0 at the vertex, or the peak here. So, and we know the slope also represents the derivative. So an alternative way for doing this problem, also, what if our initial height wasn't 0? Then we couldn't use quite the whole symmetry argument here. So an alternative solution is, what if I took the derivative, which will be this, and set that equal to 0. So t equals 5. And then, of course, plug it back in to get the height. Another way of looking at this, too, is that we know s prime is also the velocity. And the vertical velocity is going to be 0 at the peak, because obviously it's rising, but then it kind of stops rising and kind of stops momentarily. I mean, it's still moving horizontally, but the vertical velocity kind of stops for a moment and then starts dropping. So it's another way kind of like using a physics interpretation for it. Okay, part B, which I didn't leave myself enough room here. So I'll just kind of just do it right now, and you should be able to figure out what's going on here. 336 is probably going to be right here roughly. So we got these 2 points. We want to know the velocity and speed on the way up. Well, what we're going to have to do is find the times when that happens. And it's not painfully obvious at what times that happens. So what I'm going to do is set my position function equal to 336. And if I do that correctly, I should get, if I move everything over to one side, 16t squared minus 160t plus 336 equals 0. Factor out to 16. Keep factoring it. So basically I set the position function equal to 336, factored it. So we find the 2 times in which the height's 336 at 3 and 7. So what's the velocity? So in this case, we do need the velocity function. So we do need a bit of calculus here. So I'm going to find s prime of 3 and s prime of 7. And if you do it correctly, you should get 64 feet per second and negative 64 feet per second, which totally makes sense for s prime 7 because it's falling at that point. Plus, if you do tangent lines, which, the slopes represent derivatives, right? We see it's positive at t equals 3, negative slope at t equals 7, The speed, however, is 64 feet per second for both. That's because speed is the absolute value of velocity. Very important. Lastly, for part C, the answer is 10 seconds. That's because we already kind of calculated it over here. We set the position equal to 0. And when you're on the ground, s equals 0. You're at 0 position because s is representing the height above the ground. So that's what happens for C. Okay, example 5. Now, there is some interpretation of derivatives that is important. So in this case, what are the units of the derivative f prime x, and what is its meaning? Okay. So what's going to happen here is that f is going to represent the cost. So f prime x is really no different than saying dc over dx. Because if f equals c and f prime is a derivative, then we want the derivative of cost. And really, that's just going to be change in cost over change in number of figures. So it's like a slope. So the units essentially would just be dollars per figure. That would be your units. And the meaning is basically right here. Or another way of thinking about it, didn't leave myself enough room here, did I? You could say it's a rate of change of production cost. Kind of another way of looking at it. Now let's look at part B. What does it mean to say that? Well, that means that when 5,000 figures are produced, the rate of change is 14 cents per figure. Remember, derivatives are rate of change. So that's all you really need to say there. But you do have to state when you have 5,000 figures, the rate of change is that. And which one do you think is bigger? It's definitely going to be that one. That's because smaller number of figures. And remember, the denominator will be smaller, right? Since you're dividing the cost by number of figures. So that should be actually a bigger value, the change at 10. Bit of vocabulary. So we know that the derivative position with respect to time is velocity. Since we're looking at derivative cost, we call it the marginal cost. So dc over dx is called the marginal cost, which is basically the derivative of the cost function. And of course, if you have a revenue function where you're bringing in money, the derivative that's called the marginal revenue, as you see right there. Okay, just to wrap this up, let's talk about estimating a derivative from a table of values. So here we're comparing the temperature of a pond over the course of 15 days. And it looks like we're recording temperature every 3 days. And we're interested in knowing what W prime 12 is. So basically, we're trying to get the approximation of a derivative at a particular value. Now, if you were to plot the points over here, we're at 0, 3, 6, 9, 12, 15, that being time in days, and that being W, the temperature, in degrees Celsius, 10, 20, 30. The curve would kind of look like that, I guess. And if you're trying to find W prime 12, it's almost like you're trying to find the slope of the tangent line at t equals 12. So we're trying to find the slope of tangent line at t equals 12. That's what W prime 12 is going to be. Now, we don't have a sophisticated measurement tools to find the slope of that black line, and there's no equation. So what do we do? Well, here's what we do. We're going to say W prime 12 is going to equal W15 minus W9 over 15 minus 9. Why do you think I'm going to say that? So I feel comfortable in saying that because this right here, of course, is an average rate of change, which is going to be a secant line that passes through 9 and 15. Well, if you think about it, it seems as if the red line and the black line are nearly parallel. So it does serve as a good approximation. So basically what you want to do is choose two input values close to the input in question, but obey symmetry. That'd be kind of my advice for you here. So if you work it out, it's going to be easy. W15 is 21, W9 is 24. Of course, 15 minus 9 is that right there, negative 3, 6. So the answer is going to be negative 1/2 degrees Celsius per day. Let me write that more neatly. That's a little hard to read. Sorry about that. So negative 1/2 degrees Celsius per day. That's going to be the rate of change for the temperature at day 12. And then lastly, 7, which is kind of cut from the same cloth. We're trying to find R prime 45. So probably I should focus on these two values because 45 is right in between. So R prime 45, it looks like we're comparing some volume flow rates with time. So it's going to be R50 minus R40 over 50 minus 40. So it's 55 minus 40 over 10. We got 1.5 gallons per minute squared. because you're doing gallons per minute, those are going to be the proper units. Now, do we need the graphs? Actually, no. We didn't need the graphs. I mean, it's nice to see, okay, trying to find the slope of the tangent line. Let's try to draw it better. 45 right over here. Try to draw a tangent line. Kind of looks like that. That's a little better. But, I don't know. The table is all we really need. And again, choose two input values that are close to the input in question but obey symmetry. Because if you choose two input values that are too far away, like for example, if I did 0 and 90, that might not be as accurate. Whereas if I look at 40 and 50, it's about the same. So, okay, that concludes the video on the rest of the 3.4 notes.